Hello, math humans. We're going to do 3.5b today. We're going to be continuing our work with limits at infinity. So we're just going to jump right in with some examples. The first one, example number 1, says find the limit as x approaches infinity of the sine of x. So if you'll remember, the sine of x function is a periodic function, and it looks like that. So therefore, this is an oscillating function, and therefore, the limit of f of x as x approaches infinity does not exist because it is an oscillating function. Okay? Example number 2 is kind of a variation of this problem, and I'm going to find the limit as x approaches infinity of the sine of x over x. This is a special situation. You may or may not have talked about this particular type of function in pre-calc, but I could rewrite this as 1 over x times the sine of x. So if you graph this in your grapher, you'll get some stuff like this, whoop, and then some stuff like this, okay? So what's happening is the 1 over x is called a damping factor, and it's changing the shape of the graph. And if you think about it, the limit of this as x approaches infinity is going to be 0. And so what it looks like, and then kind of down here, is that the graph is approaching 0 as x approaches infinity. So the damping factor changes the appearance of the curve and is going to determine what the function is actually going to approach. So then I would say the limit of f of x as x approaches infinity is equal to 0. Alrighty, let's move on to our next example. We'll do example number 3. Move up so you can see. And example number 3 says find the limit as x approaches plus or minus infinity of x cubed. Okay, so this is kind of an interesting situation, and primarily it's because of the additional caveat. So if we think about the graph of x cubed, it looks like this. So if I consider the limit of the function as x approaches positive infinity, the graph is going to approach positive infinity. And if I consider the limit of the function as x approaches negative infinity, the graph is going to approach negative infinity. Just from the pure standpoint of the limits need to approach the same value, then because the limits don't agree, then the limit of f of x as x approaches plus or minus infinity is not going to exist because the limits don't agree. It's also not going to exist because the limits would be approaching plus or minus infinity, increasing and decreasing without bound. Therefore, the limit wouldn't exist. All right, let's do the fourth example. We have a nice short video today, and I want to find the limit as x approaches plus or minus infinity of 2x squared minus 4x over x plus 1. So if we look at this situation, we want to talk about the degree is higher in the numerator, so that means I have a slant asymptote. And my slant asymptote, if I just looked at those two terms, is going to be approximately y is equal to 2x. I have a vertical asymptote at x is equal to a negative 1. So in general, my graph, I have a vertical asymptote at a negative 1, and I have a slant at 2. So my curve is going to look something like this, give or take a little bit, right? So I probably do have x-intercepts up here at the top, but for enough for right now, this gets me what I need. Notice that the function is approaching positive infinity or negative infinity. Therefore, the limit of the function as x approaches plus or minus infinity does not exist because the function is going to increase without bound. All right, our last example, example number 5, says find the horizontal asymptote. And this one's kind of interesting. I have y is equal to the square root of 3x plus 2 over x minus 2. So I want to talk about what happens. So notice that the degree is the same, top and bottom, but the absolute value bars create a unique situation. So remember, when I have absolute value bars, that means that I can rewrite one equation and split it into two. So y is going to equal 3x plus 2 over x minus 2, but y is also going to equal a negative 3x minus 2 over x minus 2. So that means that I'm going to have a horizontal asymptote at y is equal to 3 and a horizontal asymptote at y is equal to a negative 3. So that's kind of interesting. Alrighty, that is it for today. I will see you soon.